Having known the condition, we will now go to the types. Number one of it is the SP3 hybridization. What actually happens in SP3 hybridization is that during the electronic configuration of carbon, which we saw before at the excited state, carbon is 1s2, 2s1, 2px1, 2py1, and 2pz1. 1s orbital is not used for hybridization. The reason is because it is not in the same energy level with these ones. So this is in the first energy level, but these orbitals, they are in the second energy level. And since they are in the same energy level, they can blend to form a hybrid orbital. But this one is in the first energy level. It will not partake in the hybridization. So for hybridization to take place, we consider from here to this place. Why are we considering them? If you look at them, all of them are in the same energy level. Two. You know, before you compare with another one, both of you must have something in common. That's why they say bed of a feather, it flocks together. So this one doesn't have the same energy level with this, so you can't compete with them. You can't combine with them. Since these ones have the same energy level, they can blend, they can mix together. Now, for us to achieve the SP3 hybridization, what actually happens there is that this s orbital mixes with the px, mixes with the py, and mixes with the pz. So we now have one s mixing with px, mixing with py, mixing with pz. So a total of 3p mixed. That is something like this. This mix with this, mix with this, mix. So at the end of the day, we have the SP3. And since they mix thoroughly together, none is an exception. All of them mix together. A bond will hold them. The name of that bond that will bind them together is called sigma bond. So the bond that will hold them is a sigma bond. Sigma bond. And sigma bond is represented with this sign, sigma bond. And sigma bond is a very strong bond. That is why most of the compounds that is undergoing SP3 hybridization does not react easily. Like methane, CH4. Reactions involving methane is generally slow. The reason is because of the strength of the bond. The bond that is holding it is strong, is a sigma bond. Because one of the factors that makes a reaction to occur easily is the strength of the bond. The weaker the bond, the faster the reaction. But when the bond is strong, the reaction will be very slow because there will be restriction in the kinetic energy of the reactant particle. They cannot easily collide and reaction will be delayed. But for the rate of reaction to increase, the strength of the bond have to be weakened because the reactant have to combine together at the right geometry before a product can be formed. And if they are having a strong bond, there will be a steric effect. That steric effect will prevent them from reacting. So any compound that is undergoing SP3 hybridization is, in terms of organic compounds, they are bonded together with a sigma bond. And that sigma bond is a very strong bond. So such compound does not react easily. Features of SP3 hybrid orbital. When you see SP3 hybrid orbital, there are some features you will be able to see them. Features of SP3 hybrid orbital. How do you identify that this orbital is SP3? Because a question can be given now, you'll be asked to determine the type of hybridization taking place in the compound. So one of the features of SP3 hybrid orbital is that the shape is tetrahedral. The shape is tetrahedral. That means their shape is four-sided. The example is the methane we referred to before. The structure of methane is something like this. We have a hydrogen atom. We have another hydrogen atom. We have another hydrogen. We have another hydrogen. So all these things now, they are connected to each other in a tetrahedral manner. You look at this compound, it is having four sides. 1, 2, 3, 4. That's why we say that the shape is tetrahedral. Even if you draw it in a planar form, that is carbon, hydrogen, 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 you will still see that this compound have four-sided. It's a four-sided figure. That is why we say that they are tetrahedral shape. So the SP3 hybrid orbiter, one of their features is that they have tetrahedral shape when we are referring to the hybrid orbitals of carbon. The example is the methane. Another one is that the bond angle is 109.5 degrees. The bond angle is 109.5 degrees. And what is the bond angle? Bond angle simply means distance between two bonds, or the angle between two bonds. Example, if you have this compound, carbon, hydrogen, hydrogen, hydrogen. So the distance from here to here is a bond angle. The distance from here to here is a bond angle. The distance from here to here is a bond angle. The distance from here to here is a bond angle. So the bond angle for the SP3 hybrid orbiter is 109.5 degrees. That is the orientation of the hydrogen in the methane, structure of methane. The distance between the two hydrogen, the angle there should be 109.5 degrees. So number 3 is that the bond is sigma bond. So when we see SP3 hybridization or SP3 hybrid orbiter, the bond, the name of the bond is a sigma bond. Like in this methane, all these bonds are sigma bond. And sigma bonds are very strong bonds. You don't easily break them. Because of that, this does not react. The order of reactivity of organic compound, alkyne, is more reactive than alkene. And alkene is more reactive than alkane. This reactivity is a function of their bond strength. The one whose bond is very weak is the alkyne, the ones with a triple bond. They react faster. So the one with a double bond follows. But the one that does not react easily is the one with a single bond. That is why when you come to the chemistry of alkane, you discover that the reactions, the chemical properties of alkane are just few. Basically, we have 2 or 3 of them. One of it is the oxidation reaction or combustion reaction, which is common to every organic compound, because every organic compound bonds in air, that is the hydrocarbons. They bond in air to produce CO2 and water, which alkane is one of them. Then when you talk about the next type of reaction, they undergo substitution reaction. Substitution reaction, or what you call displacement or replacement reaction. In that case, the presence of sunlight must be there. UV light must be there for them to react, because alkane, they cannot react in the absence of light. The light is a kind of catalyst that helps them to speed up the reaction rate. And in that case, it's a photochemical reaction because it takes place in the presence of sunlight. Example is the chlorination of methane to get tetrachloromethane. That reaction cannot occur in the dark. Sunlight must be there. When the sunlight is coming, it is helping to break the bond because the bond is strong. It's a sigma bond. But alkene and alkyne, they can react in the absence of sunlight because their bond is already weak. They don't need something to break the bond again. So with a little pressure, the bonds have been separated and reaction have taken place. But alkane have limited reaction. What is making them to have limited reaction is the presence of a sigma bond. It's a very strong bond. They resist reaction. Even if they have to undergo reaction, you need a catalyst. One of the catalysts, like we mentioned, is the sunlight. If the sunlight is not there, they don't react. So when we talk about the SP3 hybridization, the SP3, an easy way you can be able to identify that a compound is undergoing SP3 hybridization is to count the number of attachments on the central atom. You count the number of attachments on the central atom. If the number of attachments on the central atom is 4, it means that the compound is undergoing SP3 hybridization. Take, for instance, the number of s orbital here is 1, And the number of p orbital here is 3. That is why we say SP3. If you say 1 plus 3, it gives you 4. So anytime a compound, you see a compound and they say you should identify whether it's SP3 or SP2 or SP. It's very simple. If you are talking about the SP3, the number of attachment to the central atom must be 4 before there will be SP3 hybridization. The attachment could be a bond. The attachment can also be a lone pair of electron. Example now, if I have this compound, carbon, hydrogen, 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 and I'm asked to identify the type of hybridization taking place here, I don't need to stress myself much. What I will just do is to look at the central atom. The central atom here is carbon. I will ask myself, how many attachments does this carbon have? Of course, you see one of the attachments, number 1, number 2, number 3, number 4. So this carbon has 4 attachments. Because of that, the hybridization here becomes SP3. Because when we talk about SP3, we means the thing must have 4 attachments. That is 1s and 3p. 1 plus 3 will give you 4. So the type of hybridization this compound is undergoing is SP3. Even if I have this compound now, ammonia, NOH3, the structure of ammonia is this: nitrogen bonded to 3 hydrogen. And you know that every element tries to attain either octet or duplet configuration. So the nitrogen atom has 6 electrons here, 2, 4, 6. It's still looking for 2 more electrons to become 8. So there will be a lone pair of electron here to make it octet configuration. So now, if you are asked to identify the type of hybridization taking place in this compound, you can count the number of things attached to the central atom. Central atom means atom at the center. The one at the center here is the nitrogen. So how many things is attached to it? 1, we have a lone pair, that is 1 attachment. We have hydrogen, that is another attachment. We have this, that is another attachment. We have the other hydrogen, that is another attachment. So a total of 4 attachments. And whenever we have 4 attachments, the compound is undergoing SP3 hybridization. So ammonia is also undergoing SP3 hybridization. So when we talk about maybe water molecule, water is H2O. And the structure of water now, the element that will be at the center is the one that is alone. If you look at this compound, how you choose the element that will be at the center is the atom or the element that is alone. If you look at this place now, the compound is CH4. The atom that is single here is carbon. That is why it is at the center. If you look at NOH3, the one that is single here is nitrogen. That is why it is at the center. If you look at water molecule now, oxygen is alone, and that is why it will be at the center. So for you to choose the central atom, it is normally the atom with a lower electronegativity value, or the atom that is alone, that is single in the molecule. So here oxygen will be, we have this one. Oxygen is the central atom, then hydrogen is surrounding it. And we said that every element attains octet configuration. Anytime you see a bond means 2 electrons. That is a pair of electrons. So there is a pair of electrons here, there is a pair of electrons. We have 4 electrons out of 8. Octets have to do with 8 electrons. So since we have 4, what will now happen to the remaining 4? What will happen to the remaining 4 is that those 4 will be on the oxygen. They are called lone pair of electrons. The meaning of lone pair is that those electrons have not been used for bonding. They are still free. So we now have 1 lone pair. We have another lone pair. If you count the number of electrons here, it will become 8. 2, 4, 6, 8. So water will now be rejoicing because all the electrons that is needed for the octet configuration attainment has been completed. So we have 2, 4, 6, 8. The water is okay. Now, for you to know the type of hybridization, look at the central atom, which is the oxygen. How many attachments does it have? We have 1. This is another attachment, number 2. This is another attachment, number 3. This is another attachment, number 4. So a total of 4 attachments. And we say that whenever you have 4 attachments, that the compound is undergoing SP3 hybridization. So That is an easy way for you to know the type of hybridization a compound is undergoing, whether it is SP3. That is for SP3. Then we talk about the second type of hybridization, which is the SP2 hybridization. In the SP2 hybridization, it simply means that we have something like this: 2s1, 2px1, 2py1, 2pz1. These two. So these are the ones that are hybridizing. Hybridizing means the ones that are mixing up. So in the SP2 hybridization, what actually happens there is that the s orbital blends with the px, blends with the 2py, and 2pz did not partake in the hybridization. So those ones that mix together is this, the s mixing with this one, the pyx, then mixing with this one, which is the py. So three of them mix together, three things mix together. That is 1s and 2p. That is SP2. This other one did not participate in the hybridization, unlike the first one, which every of them participated. That is why we have S and the P3 for the first one. But this one now is SP2. What actually happens there is that the 2s mix with the 2px, mix with the 2py, but 2pz refuse to mix with them. So these ones that mix now give the SP2 hybridization. And in that case, the bond that is binding these together is a sigma bond. Now, the 2pz that is unhybridized, the 2pz that did not participate in the hybridization, will also form another bond. That one is going to be a weaker bond. The name of the bond is a pi bond. So the first one is the sigma bond, but the 2pz forms a pi bond, and the pi bond is weak. What makes it to be weak is that one thing is forming it. You know, when you have a mixture of different things, it will be stronger than when you have only one thing forming something. So this mix with this to form the SP2 hybrid orbital, and the bond they have generated is the sigma bond. Then the 2pz that is forming a bond on its own alone forms a weak bond, and the name of that weak bond is a pi bond. So we have a pi bond. This shows you that if you come to a compound and you have a double bond in that compound, that compound is undergoing SP2 hybridization. So how do you know that a compound is undergoing SP2 hybridization? One of the fastest way to check it is the number of bond. If the number of bond in that compound is 2, automatically that compound is undergoing SP2 hybridization. So apart from the number of bond, another way you can check is how many attachments does the central atom have. If the central atom have 3 attachments, like we have 1s and 2p, 1 plus 2 will give you total of 3. So anytime there is a 3 attachment to a central atom, that means that that particular molecule or compound is undergoing SP2 hybridization, apart from checking the number of the bond. So in that case now, we can cite some example. Like if you look at this compound and you are asked to identify the type of hybridization taking place in this compound, it is very simple. One thing you ask yourself is, which of the atom is the central atom? Of course, you know carbon is the one at the center. So this carbon now, how many attachments does it have? This is one attachment. Even if you have 3 bonds, we count it as one attachment because it is attached to only one thing, carbon. So this is one attachment. This is another attachment. This is another attachment. 1, 2, 3. And anytime you have 3 attachments, it means that the compound is undergoing SP2. That is 1s and 2p, 3 things. The compound is undergoing SP2 hybridization. If you consider this carbon again, you will still see the same thing. This is one attachment, this is another attachment, and this is another attachment, making it the 3rd one. So this carbon also is SP2 hybridized, while this one is also SP2 hybridized. If you come to something like benzene ring, and you are looking for the type of hybridization that is taking place in this compound. Of course, you know there is a carbon here. We have carbon in all. In benzene, what we have is 6 carbon and 6 hydrogen. So 1, 2, 3, 4, 5, 6. Carbon is already 6. Then the hydrogen, we have this, and this. 6 hydrogen. So if I'm taking this as a reference, I want to know the type of hybridization that is taking place here. This carbon is bonded to 1 hydrogen. This is 1. Another attachment he has is this one, which is 2. Another attachment he has is this one, which is 3. So the number of attachments is 1, 2, 3. And we say that anything that is having 3 attachments is undergoing SP2. That is 1s and 2p. So this is SP2 hybridized. If we pick another carbon here now, this is this carbon. The attachment we have here is 1 attachment. This is another attachment, the second one. This is another attachment. Even if there's double bond or triple bond, we count it as 1 attachment. So this is the third one. So if you count the number of attachments, it is 3. 1, 2, 3. So because of that, it is SP2 hybridized. So if a question comes this way, what is the type of hybridization taking place in benzene? The answer is SP2 hybridization. The reason is because if you come to the benzene ring, the number of attachment to the carbon is 3 attachments. 1 hydrogen and a bond this side and another bond this side, making it 3 attachments. So it's SP2 hybridized. If you don't want to use that situation, you can also use the number of bond. Any compound that has double bond is SP2 hybridized. That is, one of the bond is a sigma bond that is formed from the blending of the S and the PX and PY. Then the other bond is formed as a result of the PZ or beta that did not participate in the hybridization, making it a double bond. The features of SP2 hybrid or beta: number 1, the shape is trigonal. That is in form of triangle, like we have, or you can say trigonal plan. We can have something like this: hydrogen, hydrogen. If you complete this, it's like a triangle. You have this. This is like a triangle. It's trigonal shape. You can also have something like this. If you complete this, it is like a triangle. That is trigonal shape. Then, or you say trigonal plan. Planar means that in a plane surface. So number 2, the bond angle. The bond angle is 120 degrees. Just like this, the distance between 2 bonds. We have this. So from here to here is 120 degrees. From here to here is 120 degrees. So in SP2 hybrid or beta, using ethane as a case study, the distance between the bond, between the 2 hydrogen atoms is 120 degrees. That's why we mean that the bond angle is 120. So ethane as a compound undergoing SP2 hybridization is bonded to, one of the hydrogen is bonded to the other, to the carbon atom, and the distance between the 2 hydrogen atoms is 120 degrees. That's the bond angle. So number 3 is that we have 2 bonds. Double bond is present. Double bond is present. We have 1 sigma bond and 1 pi bond. Like here now, the compound is having double bond. One of the bond is the sigma bond. The other one is the pi bond. And we know how they are formed. That if you have 1s or beta, 2s1, 2px1, 2py1, and 2pz1, these ones mix together to form the sigma bond. Then the pz that did not follow them in the mixing forms another bond, which is the pi bond. So we have a total of double bond there. 1 sigma and 1 pi bond. That's why we say double bond is present. So these are the features we can use to identify SP2 hybridization or hybrid or beta. Okay, the last is SP hybridization. SP hybridization. In the SP hybridization, what actually happens there is that the S orbital blends with the PX to form a bond, and name of the bond is a sigma bond. What do we mean by this? If you look at the carbon atom at excited state, this is the configuration. This is the excited state of carbon atom. So in SP hybridization, what actually happens is that this 2s mixes with 2px. 1s and 1p. That is why we have sp. And both of them are bonded together with a bond that is called a sigma bond. It's a strong bond that is binding them. Then the py did not participate in the mixing. The py did not participate in the blending. So it will form its own bond. And the bond is going to form will be a weak bond, because it's only one thing that is forming that bond, and that is a pi bond. The pz also will also form its own bond, because since it is the only one forming the bond will also be weak. That is another pi bond. So if you look at this one now, how many bonds do we have? We have a total of 1, 2, 3. 3 bonds. So any compound that is having triple bond is undergoing what? SP hybridization. But any compound that is having single bond is for SP3, double bond is for SP2, and triple bond is for SP. So in the SP3, everything mixed together to give us one bond. None was left out. That's why we have a single bond. In SP2, only S, PX, and PY mixed to form one bond. The PZ that did not follow them in the mixing formed the second bond, making a double bond. But here now, we only have the 2S and the 2PX that mixed together to form the SP. Then the PY that did not participate in the bonding formed its own bond. The PZ that did not participate in the hybridization also formed its own bond, making it a total of triple bond. So one of the ways you can identify that a compound is undergoing SP hybridization is by the number of the bond there. Apart from the number of the bond, another way you can know is the number of attachment to the central atom. If the number of attachment to the central atom is 2 in the sense that we only have 2 things combining, 1s and 1p. If there is 2 attachments to the central atom, it means the compound is undergoing SP2. Then here now, if you have 3 attachments, is undergoing SP2. If you have if you have 2 attachments, is undergoing SP. If you have 3 attachments, is undergoing SP2. If you have 4 attachments, is undergoing SP3. That is 1s and 3p, 4 things. 1s and 2p, 3 things. 1s and 1p, 2 things. Now, let's take an example of the SP hybridization. If you look at this compound CO2, the element that will be at the center, or the atom that will be at the center, will be what? Carbon. Why? Carbon is alone. We say that how you select the central atom is the one with a lower electronegativity. Or, if you don't want to use electronegativity value, you can check the one that is appearing alone, the atom that is single in the molecule. So carbon is 1, so it will be the one at the center. It will be bonded to oxygen here, bonded to oxygen this side. So this is the structure of CO2, is a linear molecule. So in that case, if you are asked to identify the type of hybridization taking place here, you look at the central atom, which is carbon. How many attachments does it have? This side, it has 1 attachment. Even if the bond is 3, 4, or any number of bonds, we count it as 1 attachment. Here now is also 1 attachment. 1 plus 1 make it 2 different attachments. And since we have 2 different attachments, the compound is undergoing SP hybridization. Another example is C2H2. I want to know the type of hybridization taking place here. The element that will be at the center is carbon. It is something like this. This is acetylene. If you are taking this carbon as a reference, we want to know the type of hybridization taking place here. All this bond now is regarded as one attachment, one. So this other hydrogen is another attachment, making it two. So we have two attachments. Since we have two attachments, the compound is undergoing SP2 hybridization because there are two attachments, SP hybridization. So that is it. Whenever you have two attachments, the compound is undergoing SP hybridization. When you have three attachments, it's undergoing SP2. If you have four attachments, it's undergoing SP3 hybridization. So that is the concept of hybridization. Thank you.